Hello, Elise and Anna. It seems that the recording from class for some reason stopped at 12 minutes today. So that'll teach me to use Google Meet, and I'll only use Zoom to record stuff from now on. So let me try to summarize what we talked about today. So we had the review or the reading homework, and so we looked at B. Looking at that. So U of 8 is 1, 3, 5, and 7. So the subgroup that's generated by 3 is 1 and 3. And so cosets partition the group. So the other coset, which would be 5, 3, or 7, 3, or 3, 5, or 3, 7, is the set 5, 7. And then if we look at the part D, the alternating group on um, permitting 4 things, think of there's a couple ways to do it. Think of like the function tau, which would send any permutation to 0, 1, where it sends some to 0 if it's an even number of transpositions and 1 if it's an odd number of transpositions. Then tau of all of A4 sends everything to 0. And so then if you multiply like A4 by any single transposition, that is the other coset. So that means that because we know that they partition the group, so that means A4 is all these guys, like all these things from A4, and then the other coset, which would be like 1, 2 A4 or 3, 4 A4, whichever, it's going to be all the singleton transpositions and all the order 4 cycles. And then what did we do? We looked at so then what we did in class is that we looked at the group D4. So we looked at D4 and thought about, the symmetry of a square. And the easiest way to write it algebraically is in the RS format, where it has generators R and S. R to the fourth equals the identity, and S squared equals the identity. And when you conjugate R with 2 S's on either side, you get R inverse. So then what we did is we found all the left cosets and all the right cosets of this subgroup called H, which is generated by R squared. So it's just E and R squared. And so then we found that if you multiply on the left by R, you get R and R cubed. Multiply on the left by S, you get S and SR squared. And because these cosets partition the group, you know that the two elements that are still not covered are SR and SR cubed. So pick one of those and make that coset, and you get those last two. And then if you do the right cosets, they are exactly the same. So that's a particular thing about this group. So then a lot of our class time was spent having the students work on this. So I had them put the elements of D4 grouped by their cosets. So I put black coset, then the red coset, then the green coset, then the orange coset, and same on down the bottom. And if you kind of look just a little further away from this and just look for the colors, you might notice that it has some structure. And if you think about going back to what's called the Klein 4 group, or Z2 cross Z2, and you color your elements black, red, green, orange, and order them the same way, you get exactly the same color scheme with Z2 cross Z2 as you do for the group D4, with the color scheme going with that subgroup of E and R squared. And that's an essential thing about the group D4. So the fact that we can write it as having this subgroup E and R squared, and then the cosets of that subgroup acting like Z2 cross Z2 tells us like something about the structure of the group. And that's something that we can't always do with other subgroups. So we looked at another subgroup, the subgroup generated by S, and with that subgroup, your left cosets are here, boom, 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 boom. Your right cosets are here, boom, 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 boom. Some of them are the same, but some of them, these two and these two, are different. And so if you try to do the same thing where you're ordered by the cosets of K, then sometimes they work nicely, like here on this side, but here they don't, because the left and right cosets are different. So if I had ordered these by the right coset instead, it would have been fine here and messed up over here. There's no way to do it both ways because the left and right cosets are not the same. So that's the thing about there's certain subgroups that have left and right cosets the same, and there's certain subgroups that don't. And that's a big deal for talking about cosets. That's setting us up for why these matter, which we'll talk about Thursday. Now, so there's a couple things we want that are kind of takeaways from class today. And that's cosets are subsets of groups that partition the group. And so think about a group, you break it into equal size subsets based on usually a subgroup, and then all the things that are just like a subgroup except multiplied by a group element. When the left and right cosets of a subgroup are the same, those cosets act like elements of a smaller, easier group, which tells us something about the structure of the group. Okay, those were sort of our main takeaways from class today. And then we looked at, there's this definition of called the index. So if you have the group and its subgroup, then when you do this brackets and you have the colon here, that is saying how many cosets does that group have, does the subgroup have? And in this case, it's this subgroup had 4 cosets because those 4 colors, and we kind of colored it by coset. And so then if you had a group with, say, size 13, and you said, oh, here's a subgroup, it's size 3. No, it can't be, because if you think about its cosets, you can't make 13 as a multiple of 3, so it's not possible to have a subgroup of order 3. That's another thing you get from this idea of cosets, which is going to come up later. Now, there's only one homework question for this, what we talked about today, and but it's a big homework question. So we kind of talked about how to do it, like the meta proof, and then we talked about how to do one of the 5 parts. So I told the students that the best way to, when you have to prove that the following conditions are equivalent, the best way to do it is do like A implies B implies C implies D implies E implies A. However, some things are easier to prove than others. So it might be better to go, oh, let me get my drawing here. Might be better to go B to A, and then because you want A to C, because that's or you could do it, I already showed how to do A to B. So maybe you want to go C to A to B to D to E. And maybe you want to switch up E and D. I'm not sure. I'm not sure which one will be easier. But anyway, if you get back to the beginning, then you've proved they're all equivalent. So one of these, all of these are fine. They're just some of them can be easier than others to kind of think about, like which will be easiest to do. So here I showed, this is a proof here that A implies B, basically. So statement A, what are you doing here? All right, the statement A is that XH equals YH. And I'm changing that because if you don't want to use subscripts, then use some different letters. It's just nicer. Proofs just look nicer if you avoid subscripts. As long as you have enough letters to handle it. So then we want to prove that this equals that. And then we talked about in class, what are these things? They're cosets, they're right cosets, and what cosets are sets. So to prove the 2 sets are equals, you have to do double containment. But there's actually, it turns out you only have to do single containment here, but we'll get to that in a second. So the way to do that is you say, well, let something be in the left one. Then what do you know about it? Well, to be in here is to be equal to a little h times x inverse for some little h in big H. That's what being in the set means, is being an H element times that x inverse. So then I did some scratch work over here and figured out like the algebra for it. So I started off with W equals H x inverse, and you just got to do some algebra. And the algebra ended up being the simplest for proving this is then looking at W inverse. So then W inverse, remember when we do inverse of two elements is you change the order as well as making them both inverse. So that means W inverse would be X H inverse, which means W inverse would be in XH. Then we're using this thing, which means W inverse is in YH. So then W inverse is equal to Y H prime for some H prime in H. This is important that you like this H prime, it might be different. It's almost certainly different in some cases from the original H. What matters is that it's in the subgroup. So you can call it a different letter, you can call it K or whatever. Calling K might make it easier algebraically down here. But anyway, it's you don't know if it's equal to H, but you know it's in capital H, you know it's in the subgroup. So then take out the inverse again, and or take the inverse of both sides again, basically, and you get inverse of each one, but order swapped. And so then W is equal to H prime inverse times Y inverse. And then H prime inverse is in H because it's a subgroup. So W is in H Y inverse. And then back over here, W is in H Y inverse. So capital H X inverse is a subset of capital H Y inverse. But X and Y were arbitrary. I could just easily swap them. So that means that the sets are equal. And that shows that A implies B. That gives you one part of the proof that we're assigning for this. Okay, so hopefully that helped. And I will also share this with Katie and Matthew so that I can kind of I'm going to talk to them about this this target thing in case they don't want to do the A, B, C, D, E method. Okay. And hope that made sense. All right, bye.